Assalamu alaikum warahmatullahi wabarakatuh, and a very good morning to everyone. So welcome to today's class, and we're going to continue what we have discussed before, which is about chapter 7, which is about steady state errors. Okay, we have looked into the specifications that we have to look once we want to design the transient response, the stability. There's no point for a system to design if we didn't reach that stability. So again, you have to do the RH criterion analysis. And then the steady state errors. Okay, we want to minimize, or we want to make sure that it doesn't approach to infinity. Okay, so again, just to recap, what is steady state error? Well, basically it's the difference between the input command and the output command in a vertical manner. Okay, you look at the vertical manner. So there are several test inputs that you can have a look. The ramp, step, and parabolic. So each of these has different function, which is 1 over s, or 1 over s squared, or 1 over s cubed. So we're taking the Laplace transform. So these are the examples. Okay, if we want to design that tracking systems, and we want to identify either this tracking system can detect all of these targets. So you put those step inputs, ramp inputs, and parabolic inputs. And then we have done the evaluation for steady state. Again, when you look into to evaluate the steady state error, okay, you look at the input and output. So if it's step input, there's two possible outcomes. In this case, it's either approach to 0, or there's a finite value of the steady state error. And then this one is ramp input. There's over here, there's 3 possible output. Okay, you could see the first output is approach to 0. Okay, the second one, it have that a finite value of steady state error, but for output 3, it is the steady state error is infinity. So we don't want that one. Okay, for today's class, we're going to look on how do we derive, or how do we calculate that steady state error. Okay, so I have this notation, which is ESS. So if you could see that ESS, well, it stands for steady state error. Okay, so for this case, in the syllabus, we're only looking at the unity feedback system. So what is feedback system? Again, it's that closed loop system. Okay, and then if it's unity, meaning that, okay, if you have GS over here, the function of GS, and there's another system which is here, which is HS, so that one is equal to 1. So because of that, we usually discard the square block diagram here, and it represents the unity. Okay, this H equals to 1. So in this case, when you have this unity feedback system, okay, there are 2 ways to calculate that steady state error, ESS. So it's either you look into the closed loop transfer function, which is T is equal to C, which is the output, over R, the function of R, which is the input. So if you could remember, if there's a single system, and then there's the output goes here and input here. So that transfer function is called closed loop transfer function, where we're taking into consideration this one is a single system. So if it's closed loop transfer function, it's C, which is the output, over the input R. Okay, that's the first one. The second one is open loop transfer function. So in this case, what do is that this is an example of open loop transfer function. This is your transfer function, and it is it's basically is the output over the function of the error here, so C over E here. So that's two ways to calculate that error, steady state error. So we're going to look on how to derive that. Okay, so if you could see here, okay, to find the error function, it is the error between the input, which is R function, and the output, which is C function. We can write it as this one, where error is equals to R minus C. So if you could see here from this block diagram, you want to calculate this error. So it's basically the R minus C here. Okay, R minus C. So apart from this equation, we actually know what is the C here. We can easily find it. Again, looking at this one, C equals to this part. And so if you're looking at the closed loop transfer function, your C is basically equal to R, which is the input, times with the transfer function. Then you simplify it and solving for the error from here. Okay, error function. You want to simplify it, you just substitute C, put it in here, and you will get this by rearranging the equation. Okay, so you will get this equation here. This is what you're looking for. And then although the equation here, okay, allows us to solve the error in t function or time domain at any time t, but we are interested in the final value of the error, E infinity. What does that mean? Meaning that, okay, we're looking at the error in time domain. So to make it easier for you to calculate, you just need to apply that final value theorem. So applying the final value theorem, we're letting the t approach to infinity. So this t is equal to infinity. Okay, once you have the t equals to infinity, you will get this one. Okay, you need to take that limit, t approach to infinity and et. Again, the Laplace transform of this et is SES here. Okay, and the limit, if it's t approach to infinity, meaning that your s is approaching to 0, and in this case your e is actually this one. Once you have calculate, once you have get this form of equation, you just need to substitute in this equation. Okay, so basically the error is equals to S is from here, and this one, the res, is from this equation. So there you have for this one, by looking at the closed loop transfer function. Okay, this one is the first step. And then the second step is that, okay, again, to find the error, which is the error between the input RS and the output CS, we can write R minus C. That is the error. Okay, looking at the diagram again, you want to calculate the error. Is basically C, R minus C. Okay, R minus C. But what is the difference is this one. Okay, the last part we're looking at the closed loop transfer function. This time we want to look at the open loop transfer function. So in this case, C is actually EG. Okay, and then what you need to do is substitute this C is equal to this one. Okay, and then simplifying and solving for ES, we can yield this equation, this form of equation. So now we apply that final value theorem. What is that? Okay, again, we want to t approach to 0. Once it's t approach to 0, meaning that as approach to 0, it does t is approach to infinity. What? So it's basically the same as approach to 0. So you just need to substitute this form equation, and once you substitute that, you will get this equation. So this one is what you have to understand. Okay, once you have this equation, remember this rs is referred to the input. Okay, so you will get different value of error if different input is considered in here. Okay, so we want to look here. Okay, so the nature of steady state error corresponds to the input Rs is determined by substituting the input. So if let's say your input is step input, Rs is equal to 1 over S. This ramp input is 1 over S squared. Parabolic input is 1 over S cubed. So what you do is, again, look at this equation. This equation, you just need to substitute the input. So it can be step input, ramp input, or parabolic. So R will be different for each input. Okay, so you could see here I've already substitute this one. Okay, and if you could see here as and as, it can be cancelled. So basically you will end up like this equation. This limit, you're taking limit of s approach to 0. And so 1, it's a constant, but this one we're taking limit at gs here. Okay, same goes to ramp input. If you have ramp input, you just substitute in the equation and we can cross out, but that's leaving another s, 1 over s. So what you do is just expand it. Again, s approach to 0, meaning you just substitute s equals to 0, and because of that you're leaving this form, whereby you're taking the limit with s approach to 0 for s gs. Okay, and same goes to parabolic. Okay, 1 over s cubed. Okay, you can easily cancel this out, but that's s squared, leaving s squared behind. You expand it, become like this, and once you take that limit s, you just replace s by 0, but we don't want to put this s equals to 0. With putting it with the constant, there's a constant that we're going to look into. Okay, so these are the errors, steady state error, once we have considered the step input, ramp input, and parabolic input. So moving on to the next one is about static error constants. Over here. Okay, steady state static error constant, which is there's a constant Kp, Kv, and Ka. So we're going to look what are those. Okay. Okay. This is the steady state error. Okay, the performance specifications are called static error constants. So basically you have this, there's a constant, okay, that will determine your steady state error, which is this one. This equation we have derived it from the last one, if you could remember. So what I have highlighted here is what basically you once you understand, you will remember it. Okay, so these are basically the steady state error corresponds to this type of input. Step input, you will get this. Ramp input, you will get this. And parabolic input, you will get this. So all of these are steady state error. But again, here, what if you could notice, we're taking the limit of the function g here. So basically you can just equate that into equal to kp. Okay, we can analyze that further. And then same goes to this one, kv, a constant kv, which is equals to down here, and ka is equals to down here. So since the static error constant here, static error constant refers to kp, kv, and ka, it appears in the denominator of the steady state error. If you notice, it's at the denominator. So the value of steady state error decreases as the static error constant increases. So it's inversely proportional. ESS, or the steady state error, will decrease once this constant is increased. So it's the other, it's the opposite way. Okay, increase, decrease, 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 and increase. Okay, so this is what we have equated before. Kp is equal to this, kv this one, and ka is that one. So if the question asks you find that static error constants, so this is what you have to do. The position constant kp is equal to this one. Okay, the velocity constant kv is equal to this one, and acceleration constant ka is equal to this one. So if you could notice here, they are merely the same. Okay, merely the same, almost the same, but what is different is the number of s here. Okay, so this one there's no s, this one s, and this one there's 2s, or you could say s squared. Okay, the number of s here represents the type of the system. So type 0 meaning that there's no s. Okay, type 1 meaning that there's 1s, type 2 meaning that there's 2s. So note that kp, kv, and ka has different number of s to be multiplied with gs. Okay, therefore an steady state error can be determined by the number of poles at origin, or the number of 1 over s in the transfer function. So this one, the steady state error, which is referring to this one, the last slide. Okay, this one. So what it states here, ESS can be determined by the number of 1 over s. Okay, if you're looking at this one, okay, how many s involved here? This one is 0, this is 1s at the bottom, this is 2s at the bottom. Okay, so those are the static error constant. And if you ask me in this chapter what are the important equations, I would say this one. It's a simple one. Once you understand, you know how to use it. It's important for you to know how to use it. And another equation is how to calculate the the steady state error here. Okay, it's just a matter of, if it's step input, you will have this one, ramp input this one, and parabolic input is this one. It doesn't have much different, it's just that as that is different, and for step input it have 1 plus something here. Okay, so we're nearly done. This one I just want to put it in easy way to represent the relationship of all of this, the relationship of the input, and then the system type, there's type 0, type 1, type 2, and then your static error constant, which is kp, kv, and ka for each of the type. Okay, and the steady state errors. So this is the steady state errors. So basically this is the formula that we have looked before the last slide, to get this formula, it's actually from this one. We have derived it from this one. You just need to substitute the input, step, ramp, and parabolic. Once you substitute it, you will get this one. Okay, so if it's type 0, okay, if you could notice here, it will give you a value, a constant value. Okay, you have that value of kp. So this value of kp will give you a finite value of the error. But for kv and ka, type 0, it will give you 0. Type 0, it will give you 0. And because of this, again, to determine the error, it's 1 over kv. So once this one is 0, okay, you will have the error equals to infinity. 1 over 0, you will have the error equal to infinity. That one is type 0. Then type 1, it's how you locate it. The kp, the value of kp will get infinity. kv is constant. You have that constant value, meaning that there's a value for kp, but ka will give you 0. And so again, you just substitute in here, kp in here. Okay, 1 plus infinity is infinity. 1 over infinity will give you 0. Okay, and then the kv, it have the value of constant. Once you substitute, it's just 1 over kv. There's a value there, and then ka, a constant, will give you it is equal to 0. So once you substitute it, you will get that infinity. And same goes to here, type 2. Okay, you can look into that one. And this one is another thing, how to represent or summarize this chapter. Okay, so you have this feedback system, unity feedback system. We are looking at those, this type of system. And if you could see here, RS, it can be either step input, ramp input, or parabolic input. So each of these, 1 over s, 1 over s squared, and 1 over s cubed. So the GS, okay, for the GS, it has 3 different types. Type 0 is where a system with no poles at the origin. But type 1, a system with 1 pole at the origin, and type 2, where a system has 2 poles at the origin. So these poles are different in terms of that, of how many poles at the origin, meaning that your S equals to 0. And then this one is to evaluate the ES, okay, the function of ES error at the steady state when S approaches to 0. So basically, most of the books, they put it in this way. Okay, so this one is some of the exercise. You can do it. It's actually in the textbook. You can have a look of how to calculate, in this case, evaluate the static error constant, and then find the expected error for the standard step, ramp, and parabolic inputs. So each of this one is actually, there's 1, 2, 3, okay, 1, 2, 3 system, different systems. So each of these, you need to do the step, ramp, and parabolic. I will make this as your assignment too, so that if you get involved in doing the exercises, you will know better. Okay, so it helps you in the examination as well. So with that, we would like to end our class, and I wish you a happy holiday, and to those Muslims, Selamat Hari Raya Aidil Adha. Okay, with that, thank you for coming. Assalamualaikum warahmatullahi wabarakatuh, and goodbye.